Welcome to Understand Chemistry. This is Dr. Bilal. In this video, we will dive deep into the mechanism and kinetics of emulsion polymerization. Emulsion polymerization is a heterogeneous free radical chain growth polymerization process conducted in an aqueous dispersion medium. Let us see the difference between suspension and emulsion polymerization. Both suspension and emulsion polymerization are heterogeneous free radical chain growth processes carried out in an aqueous dispersion medium, but with important distinctions. Oil-soluble monomers, styrene and vinyl chloride, for instance, can be used in both methods. In suspension polymerization, the monomer is distributed into droplets and held in suspension by stabilizer molecules such as polyvinyl alcohol. The initiator is oil-soluble and added directly into the monomer. The final product consists of single polymer chain, a low molar mass, and a large particle size ranging from 50 to 500 micrometer. On the other hand, emulsion polymerization takes place in micelles, which provide static stability and uniformity which cannot be achieved by suspension polymerization. These micelles are formed by surfactant molecules added to the aqueous phase prior to polymerization. Next, a water-soluble initiator is included and the growing chain becomes trapped in the micelles. In contrast to suspension polymerization, the end result consists of several polymer chain per particle. The particle size range from 0.05 to 5 micrometer. Now let us see the fundamental components of emulsion polymerization. First we have the monomers. These are the oil-soluble monomer like vinyl acetate, methyl methacrylate, styrene, vinyl chloride and butadiene. The second component is the dispersant, which is simply water. Water from the continuous phase. Initiator suitable for emulsion polymerization is inorganic water-soluble thermal initiator like potassium persulfate. The last component of the emulsion polymerization is the emulsifier or surfactant, for example sodium dodecyl sulfate. Dodecyl means 12. This means this is an amphiphilic molecule with polar head sodium sulfate and 12 carbon containing hydrophobic chain. To understand the mechanism of emulsion polymerization, it is important to first understand what a micelle is. Micelles are self-assembled nanoparticles formed from amphiphilic molecules such as sodium dodecyl sulfate. These molecules have two distinct parts, a hydrophilic polar head and a hydrophobic hydrocarbon tail. When sodium dodecyl sulfate is added to the water, the molecules initially accumulate at the water surface and reduce surface tension of water. When the surface tension of water is reduced to a level, at this stage, any additional amount of surfactant go inside water. Once the concentration of sodium dodecyl sulfate reaches a certain threshold known as the critical Micelle concentration, the amphiphilic molecules spontaneously self-assemble into spherical structures called micelles. The driving force behind micelle formation is the hydrophilic interaction of the polar heads with water, which keep them oriented outwards. Meanwhile, the hydrophobic tail avoid contact with water and instead interact with each other through the hydrophobic effect. These combined forces lead to the formation of stable spherical micelle, which are the primary site where polymerization begins. Let us look at a typical recipe for emulsion polymerization. We begin with water as the continuous phase, into which we disperse our monomer. In this case, we have styrene. To stabilize the monomer droplet, we add a surfactant, sodium dodecyl sulfate. This amphiphilic molecules form micelles once its concentration exceeds the critical Micelle concentration, allowing monomer to be solubilized and polymerization to occur inside micelles. Next, we introduce an initiator, which is potassium persulfate. Potassium persulfate decomposes thermally to generate sulfate radicals. These radicals initiate polymerization inside micelles or in the aqueous phase, leading to the formation of polymer particle. Finally, after the reaction is complete, aluminium sulfate may be added to coagulate or flocculate the latex. depending on the desired application or purification step. Now let us see what is the mechanism of emulsion polymerization. The most classic mechanism of emulsion polymerization is micellar nucleation, also known as the Smith-Ewart mechanism. This mechanism kicks in when our surfactant concentration is above the critical micelle concentration. Now let us follow the process visually. First you can see monomer droplets suspended in water. The monomer molecules dissolve slightly in water and diffuse from the droplet towards the micelle, swelling them with monomer. Simultaneously, water-soluble initiator like potassium persulfate decomposes to form radicals. Because of their immense total surface area, these radicals are statistically far more likely to enter a monomer-swollen micelle than a large monomer droplet. Once a radical enters a micelle, it finds a high local concentration of monomer and begins to polymerize rapidly. At this moment, that micelle is transformed into growing polymer particles. This process of radical entry and conversion of micelle into polymer particles continue until all the surfactant is used up. In addition to radical initiation in the micelles, some radicals attack the monomer in water phase to form oligoradicals that can also diffuse into the micelle to start polymer chain. Now let's turn to the second major nucleation mechanism, homogeneous nucleation. This is the dominant pathway when our surfactant concentration is below the critical micelle concentration, meaning we have no micelles. Also, when we have more hydrophilic monomer. This process starts as always with our water-soluble initiator, potassium persulfate, decomposing to form anionic radical in the aqueous phase. These radicals then begin to attack the monomer molecule that are dissolved in the water. They grow chain by chain, forming what we call oligomeric radicals. As these oligomers grow longer, they become increasingly hydrophobic. Once they reach a critical chain length, they can no longer stay dissolved. They precipitate out of the solution, collapsing on themselves to form what you see here as a primary particle. This primary particle is tiny, unstable, and has a poorly developed core. It quickly undergoes limited coagulation with other primary particles and absorbs surfactant molecule from the water. This process forms a stable mature particle nucleus. Finally, this mature nucleus swollen with monomer diffusing from the large droplet and becomes a fully grown polymer particle ready for steady growth. Let us see how emulsion polymerization progresses. The progress of emulsion polymerization proceeds through three intervals. We begin with interval 1, the nucleation phase. This is the startup period where the action is fast and dynamic. The number of polymer particles increases rapidly as micelles or precipitated oligomers are converted into new particles. Because we are creating more and more active reaction sites, the overall polymerization rate rises sharply. During this time, the surfactant is being depleted from the solution as it absorb onto all these new particles. This interval is typically short, ending when the surfactant is used up and the final particle count is locked, usually around 2 to 15% conversion. Interval 2 is the steady growth period. Here the particle number is constant. Monomer droplets are still present, acting as reservoirs to keep the concentration inside the particle stable. This results in a constant high rate of polymerization. It is during this phase that gel effect often emerges, where the high viscosity inside the particles slow down termination, leading to very high molar mass. Finally, we reach interval 3, monomer depletion phase. During this period, the monomer droplets disappear and the particles must consume their own internal supply of monomer. As the concentration drops, the polymerization rate decreases steadily until the reaction completes. The entire process is engineered to produce our final product, spherical polymer particles, typically 50 to 300 nanometers in diameter, suspended in water to form a stable latex. The rate of polymerization Rp at any instant is given by the product of the concentration of active particle P and the rate of propagation in the particle. The unique part of emulsion kinetics is how we define the radical concentration. We express it as the product number of latex particle per unit volume N prime and the average number of radical per particle N bar divided by Avogadro number. Combination of these two equations yields polymerization rate as shown here. Now let us see how this plays out across the three intervals. In interval 1, at the very start, there are no particles yet, so N prime into N bar is essentially 0. As nucleation progresses, the number of particles N prime drops dramatically and N bar begin to rise, causing the overall rate Rp to increase sharply. In interval 2, the particle number N prime has reached its steady state value, which we simply call N. The average number of radicals per particle N bar may or may not become constant, but it is this value N bar that becomes critically important for determining the rate. Finally, in interval C, N bar remains roughly constant, but the monomer concentration inside the particle drops, causing the rate to fall. The behavior of N bar during interval 2 and 3 leads to the famous 3 cases of Smith-Ewart kinetics, which ultimately dictate the final reaction rate. Smith-Ewart case 1 in emulsion polymerization, where the average number of radical per particle denoted as N bar is equal to 0.5. In this case, radical desorption does not occur, means no radical come out of the particle. Our radical comes out of the particle is negligibly small compared to the radical diffused in, also called absorption. So radicals stay inside the particle until they terminate. Let us walk through this sequence. First, a radical enters a micelle containing monomer. Polymerization begins inside the micelle, forming a growing chain. At this point, the micelle becomes a polymer particle with one active species. Now, if another radical enters the system, chain termination occurs and the particle becomes dormant or inactive. It has 0 active species. Later, a new radical may enter again, initiating another propagating cycle. This cycle of activation and termination continues, with each particle alternating between active and dormant states. This is known as 0-1 kinetics, meaning that each polymer particle contains either 0 or 1 radical at any given time. On average, across all particles, half of the particles are active and half are dormant, giving us N bar is equal to 0.5. This balance is crucial for maintaining high molar mass and controlled polymer growth. In Smith-Ewart case 2, the average number of radicals per particles N bar is less than 0.5. This means that the radical desorption from particles and termination in the aqueous phase are not negligible. Since radicals do not stay entrapped, many particles never become active. The polymerization rate is low because termination in solution occurs before radicals reach to the interior of particles. The molar mass is also low due to elevated termination rate. Conversely, in Smith-Ewart case 3, N bar is greater than 0.5. This happens when particle sizes are large or the termination rate constant is low, causing chain termination to fall behind propagation. Consequently, some fraction of polymer particle must contain 2 or more radicals, often leading to higher probability of bimolecular termination. The system shows a constraint on growth, slow termination leading to higher molar mass and broader distribution. In practice, Smith-Ewart case 1 is the most common scenario in emulsion polymerization. The true power of emulsion polymerization is revealed by the vast number of commercial applications, many of which are part of our daily lives. First, in paints and coating. This process gives us water-based latex paints which are popular for their ease of use, low odor and fast drying times as well as durable industrial coatings. Secondly, it is used in adhesives and binders. It produces the essential polymers for paper and packaging coating, which provide strength and smooth finish and strong construction adhesives used in flooring and paneling. And the third and perhaps most significantly, it is the foundation of the synthetic rubber industry. The styrene butadiene rubber or SBR made through emulsion polymerization is a primary component in car tires as well as products like gloves and seals. For further readings, I highly recommend the article published in Biomicromolecules by Lowell and Schoch. It provides a thorough and insightful explanation of emulsion polymerization, including mechanistic details, kinetic models, and practical considerations. Thanks for watching.